It happens.
Alright, a rational function is a quotient of polynomials.
Define quotient real quick.
Quotient is just division.
Thank you.
You just got a fraction with polynomials in the numerator and denominator. Okay? So for example, you might have like 3x to the third plus 2x squared plus 5x plus 4 over 2x squared plus 3x plus 1, something like that.
Is that all?
So you got a quotient of polynomials. You got a polynomial in the numerator divided by another polynomial.
Okay.
Okay? Now, one thing we want to talk about is how to graph these things. Okay, how do we graph them? You guys know the graph calculator open? Okay? The most important thing when you're graphing is you must put parentheses around the numerator and the denominator. Okay? So when you're graphing this, parentheses around your entire numerator and your entire denominator. Okay, so if I'm going to graph this, start with parentheses. Put the entire numerator in parentheses, divide by the entire...
Where are you getting that number from?
I just made it up.
Oh, okay. Who's putting in that one you put in?
What number?
That one you just had up. That one.
That's what I put in.
Is that an 8?
It's a 3.
Oh, well, 3, 8, it doesn't matter. I'll just treat it like an 8. It doesn't matter, you guys. I just made that up. It's not going to look very good. Okay, so you've got to put those parentheses there.
Wow.
And the graph of these things looks really weird. Okay? They've got these vertical lines through the graph. Now, what do we see on the table here? -1 does not exist. X does not exist at -1. Now, you see where this vertical line is? It's kind of off from -1, but it's more or less at -1. The vertical lines here are going to happen where your y values don't exist. Okay? Because the graph gets to that point, it tries to calculate the y value, and it says, oh, I don't have a y value. So it doesn't know what to do, it just makes that vertical line.
Explain that a little bit.
So the vertical lines in your graph, you see that vertical line there at -1? That's going to happen at the x values that don't exist.
So
the x value is where the function doesn't exist.
So that would be the domain of your function.
Yes. Yes.
So when it's blank, that's the domain?
Well, those are the y values that the function doesn't exist for. Okay? to plug in that x value, you can't do it.
Can you tell me why my graph was totally different than yours?
You probably didn't put the division sign between the two
have to-
parentheses, because that's what I did. I didn't put the division sign between them.
That's true, yeah. That's
Where is it?
in the middle here. Just do the slash and
Oh, okay.
or right there. Okay, so I've got a hole at -1 here in my table, and then the graph makes a vertical line at -1.
It's not truly on the -1.
It is. It'll always look a little bit off on the calculator, but in real life it is on the -1 because that's where the hole in my table is. Now really the graph shouldn't be drawing that line at all. Okay, because the graph shouldn't exist there. I've got a hole in my table, there's no point there. Okay? It draws it there because it doesn't know what to do. If it gets to a point and it says, uh-oh, I can't cross this point, I don't know what to do, so it just makes like a vertical line. Okay, now John said the word that is causing those lines, which is the domain. Now what can we not have in a rational function? Can't have 0 in the denominator. Okay? Okay, you cannot have the denominator equal to 0. Okay, your function does not exist. For x values that make your denominator equal to 0. So if I want to find my domain, I need to figure out what x values would make that denominator equal to 0, because those are the ones that I can't have.
Which should be the one that comes up as blank inside the...
There may be others though. Because remember your table is only showing you whole number increments. So there may be others that are fractions. So let's go back to our example here. Let's find the domain of this function. Okay, so for the domain, you do not care about the numerator. You don't care about it at all. You only care about that denominator being 0. Okay? So let's take our denominator, set it equal to 0, and solve for x. Now, how can I solve this for x if it's a quadratic? You can factor it, okay? So this will factor. Okay, it's actually going to factor to 2x plus 1 times x plus 1. Okay, then I want to set those factors equal to 0. Okay, I'm going to get x equals -1. And then for the other one, I'm going to get x equals -1/2. So -1 was the one that we could see in our table. -1/2 is another one. So for my domain, okay, I would say all x except
since the negative 1/2 comes first, why does it stop it there instead of going to the negative 1?
It can actually, it can jump over those points.
Because it looks like it tried to at the negative
And that's where
1/2.
you're getting those vertical lines. I'm getting a vertical line here where it's trying to jump over -1, and then it's going vertical here. It doesn't go all the way down, but it's going. You see that little vertical dip right here where it gets to 1/2, but then it can jump over that and keep going. Okay, so for the rest of my graph, I get normal looking points. Okay, so if I actually change my table setting where my step is 1/2, then I'll see that other empty spot. If I want to go in increments of 1/2, then I can actually see both of them, -1 and -1/2 are both non-existent. Okay, so sometimes you can pick those points out of your table, and sometimes you kind of have to know where they are so that you know where to look for them. Okay, so you always, for the domain, you always want to set your denominator equal to 0 and solve for x. Okay, and then once you find those x values, then x cannot equal these numbers. Everything else is okay. Okay, so what happens at those x values?
The function is, yeah, it just doesn't
It
work.
doesn't work, okay? At points where the denominator equals 0, the function doesn't work. Okay? But you'll see one of two things happen in the graph. The first one that can happen is it'll show like a vertical line. Okay? So that's called a vertical asymptote. You guys heard that word before?
No, I just seen that.
Asymptote means just a vertical line. A-S-Y-M, you just write it. A-S-Y-M-P-T-O-T. Well, that's what usually happens, is you'll have a vertical asymptote, which is just a vertical line, kind of an invisible line, that your function can't cross in that graph. Okay? Now there's one exception to that rule, and that's when your x value then it's almost kind of like that point kind of cancels itself out. You get 0 on top and 0 on the bottom. And what happens there is you have what, just like a hole in the graph.
So this is the time when we actually would pay attention to the numerator?
Yes. Because if you look at the graph and you're not seeing a vertical asymptote, you're not seeing a vertical line, it'll just draw straight through that point. Okay, then it's not an asymptote because it's not going vertical at that point. It's just kind of a missing point.
Do you have a formula that will graph that? For example?
A formula? We'll do a couple examples.
Okay.
Okay, so for an example, let's do this in groups or individually on a separate sheet of paper. Let's keep that function, let's keep the denominator of that function the same. Well, let's make the numerator a little bit simpler. So let's take the numerator down to a linear function of 2x plus 1. Now, I kept the denominator the same here because we already know the domain. Okay, we know that -1 and -1/2 were the excluded point, because those make the denominator equal to 0. Okay, now let's look at those 2 points and see what they do to the numerator. Do either of those make the numerator equal to 0?
Yes.
Yes. Which one?
-1/2.
Okay, -1/2 also makes your numerator equal to 0. And you can see that because when you factored your denominator, factor to 2x plus 1 times x plus 1. Okay, you see that factor occurring in the numerator and the denominator. So you know the same number would make those 0. Okay, it's almost like that kind of factor kind of cancels out. You don't really want to cancel it out, but it does sort of cancel out. Okay?
So you're saying that would actually be a 0.00, maybe?
No, it's still not going to exist in the graph.
Okay.
Okay? So what's going to happen you'll have a hole at -1/2, but -1 doesn't do anything to the numerator. Okay? That other point that's excluded. So that other point will be a vertical asymptote.
So we just gonna call those holes?
Yes.
Okay. I like that.
But that,
Okay? Now let's look at the graph of this thing and see what it looks like on the graph. So keep your graph the way it already was. Keep your table at depth of 0.5. And just erase that numerator you already had in there. And you guys are following along with me, so you guys are probably doing your own problems.
still has the negative one,
So the negative one still has the vertical line, so it's still a vertical asymptote. But now I don't see that at negative 1/2. It just draws straight through it. Okay, so I don't see anything vertical happening at negative 1/2, but it's still missing in the table. Okay, that's why it's called a hole, because it's a hole in your table, but it doesn't show up in your graph necessarily. Now you see it's got a little, kind of a little blip there where it thinks something's wrong there, but it'll just draw straight through those holes. The vertical asymptote will actually produce a vertical line. Okay, so really you've got this vertical asymptote here. And you should just have like a little empty spot here.
What you do, it's 2 points.
Yes.
You
But
could-
it just doesn't know how to draw that little empty spot, so it just draws right through it. Okay, let's look at a homework problem that asks us to find vertical asymptote. Anybody find one?
Five.
Number 5.
No, it's vertical.
It has horizontal too.
Well, we're going to talk about horizontal separately. Okay, so my equation is 1 over x minus 4. Is there one that just talks about vertical?
I don't think so. None that I've checked.
Okay, so how do I find my vertical asymptote here? I want to
You need to find the domain.
find the domain, right? Vertical asymptotes are related to the domain. So to find the domain,
Possible.
I want to say x minus 4 cannot be 0. Okay, so my domain would be x is not equal to positive 4. Positive 4 would make my denominator equal to 0. Now, does that make the numerator equal to 0?
No.
The numerator can't be 0. It doesn't have any variables. There's nothing to plug in there. So the numerator can't be affected by that, so we're going to have a vertical asymptote. Usually the ones with holes, it's a big tip-off because it'll have multiple choice in this problem. Like one of the choices will be there is a hole at such and such. So if you don't see that, chances are there's not a hole in the graph. Okay, so I just want to answer vertical asymptote at x equals 4. Now what are horizontal asymptotes?
There are the holes.
They're not the holes. Holes are just not holes. They
It would
are.
be horizontal.
They're the horizontal lines that run through your function. And they're kind of invisible, so you kind of have to look for them. Do you guys see any horizontal lines that would run through my function? Here?
Is it where it kind of tapers off and
Mhm.
runs flat against the?
That's a good way to put it. It's where it kind of tapers into a flat line on either side. Do you see how this kind of goes horizontal? If you look at both ends together, there'd be kind of a horizontal line running through it.
So that would be on the x line then, right?
In this case, it's at the x-axis. It's not always the case.
So the y-axis is 0, basically.
Right, y equals 0 would be the x-axis. Okay, there's three possibilities for horizontal asymptote. Okay, now you have to just know these rules. There's really no way to get around this. It's just rules you need to have written down in your notes that you can refer to. They're related to the degree of the numerator and the denominator. Okay, what do I mean by degree again?
Or the exponent.
Highest exponent, yes.
Okay. Okay, almost done. How are they related?
The degree determines whether or not you have a horizontal asymptote and whether or not, or where it's actually located.
So would an odd degree result in a horizontal asymptote?
No. Let me write them down.
Okay.
There's 3 possibilities. If you guys want to guess what the case is, we would be here for a while. 3 possibilities. The possibilities are you can have a higher degree in the numerator. You can have a higher degree in the denominator. Or you can have the same degree.
Well, that covers basically everything.
That covers everything. Higher on top, higher on bottom, or they're the same. There's no other possibility. Okay, higher degree in the numerator is when you do not have a horizontal asymptote. Now in this case, if you don't have a horizontal, then you will have something else, the third type. This is called a slant asymptote.
That's
A slanted line through your function, okay?
basically a slope.
A linear asymptote, yeah. They're called slant asymptotes. Sometimes the fancy word for that is oblique. OBLIQUE. So I usually try not to use that word, I just call them slant. But sometimes you may see your homework may, on rare occasions, use that word. It means the same as slant. In the case where you don't have a horizontal, you will have a slant asymptote in that case. Okay, what if we have a higher degree in the denominator? That's where you have a vertical asymptote. Not vertical, horizontal, sorry. At y equals 0. Okay? Because if you've got a higher degree in the denominator, then the denominator is getting bigger faster. So your fraction's just going to get smaller and smaller and smaller. It's going to approach 0. If your denominator is getting bigger faster. Okay? Y equals 0 is the x-axis.
Just
If you see a function that's going towards the x-axis, like the one that we looked at a little bit ago.
Is it always going to be at the x-axis?
If you